Okay, so today, when you're working on this definite integral, we'll be using Riemann sum. I hope you are able to look through those formulas, right? Left, right, and midpoint Riemann sum. What we have noticed is, listen carefully, when we were working on Riemann sum, one thing we have noticed is we can find the Riemann sum using the left side of the rectangle, we call it left Riemann sum, or right side of the rectangle as the height, we call that right-hand Riemann sum, or we can also find the height from the middle of the rectangle and we say midpoint Riemann sum, right? We can use these three different concepts to find the Riemann sum. But what we have noticed is if we take the midpoint Riemann sum, our result will be more accurate. That's one thing we have seen. Okay, midpoint Riemann sum will give you more accurate result compared to all three, right? Midpoint Riemann sum give more accurate result. Also, the other thing we have noticed is whether we are working on left Riemann sum, right Riemann sum, or midpoint Riemann sum, if the number of rectangles we are taking, or if we divide that interval into a smaller number of sub-intervals, the result is not that accurate. If we increase the number of intervals, then the result will be more and more accurate. That means if we can make n very large, or n goes to infinity, then the area will be 100% accurate. Okay, so that is what we are doing today. We are calculating the definite integral using the limit of Riemann sum. So we are calculating the definite integral using, I'm writing there inside that box, using limit of Riemann sum. That should be the topic. Using limit of Riemann sum, definite integral using limit of Riemann sum. So if you look there, what I have is, if there is a function y equal to f of x, defined on the interval from x equal to a to x equal to b. We can quickly draw at the side to represent that. So let's draw it. We can represent this here. Suppose my function is this one. Suppose that is y equal to f of x. Okay, y equal to f of x. And it is defined on this interval from x equal to a to x equal to b. So we can also show that. So from x equal to a to x equal to b. Okay, a function is defined there. And if I want to find the definite integral here, if I want to find the definite integral, say for example, definite integral from a through b of the function with respect to x, that will be equal to this area. Okay, definite integral will be equal to that area. But we have not studied how we can evaluate any definite integral so far. But what we have done is we learned how to approximate this area using the Riemann sum. And if you look for that area approximation formula for Riemann sum, it is this one here, right? Summation k goes from 1 through n. That is, we are counting these rectangles. We have n rectangles from 1 up to n. N can be 10, n can be 20, n can be 30, n can be any number of f of xk times delta xk. We know how to find that delta x or delta xk, however you want to write it. And also based on left, right, or midpoint Riemann sum, we know how to find xk. Then when we take the sum, we get the approximate area. Okay. And what we have said in the previous class is, if we can make those interval really, really small, that is, if we take the limit as delta x goes to 0, if the interval is very small, then the number of rectangles will increase, right? That will give you more accurate results. So we can write it as limit as x approaches to 0 of this function. Or You can equivalently write this as, we can also write it like this. That definite integral is also equal to, let's write it down here. This is equal to limit as n approaches to infinity, right? When the size of the interval becomes very, very small, the number of intervals will go to infinity. Limit as n approaches to infinity of that same function there. Summation k equal to 1 through n, f of xk, we can just write delta x or delta xk, it is same thing. So today what we are doing is, in order to find the exact value of the area, one more time, in order to find the exact value of the area shown here in this diagram, or the definite integral from a through b, we'll be using the limit of Riemann sum. We'll be using that equation. Okay, we'll use that equation and find the area. But when we're doing this, it involves a lot of summation, a lot of formulas there. So we are going to talk a little bit about some of these formulas that you see here. And these formulas will be useful when we try to evaluate the definite integral. So we are going to look at sum of positive integers. Okay, let's look at some of these important formulas here. Let me get a new page here. Okay. So what we are looking at is, we are looking at sum of positive integers. That is what we want to explore first. Let me write sum of positive integers. You already have that in your note catcher. I am writing it here. Okay, first of all, let's talk about the sum of constant. That is, we write like this, summation, sum of constant from n equal to 1, or I will write k equal to 1 just to make it similar to your note catcher, k equal to 1 through k equal to n. You need to know the meaning of that. When I say sum of constant from k equal to 1 through k equal to n, meaning of that is I am adding this constant, okay? I'm adding this constant c n times. That is the meaning of that, okay? So if I want to write the meaning of that, it is c plus c plus c plus, we are doing this n times. Okay, we are adding that n times. And the result is, if I add 2 times, that will be 2c, right? C plus c, 2c. If I go up to 3, then it will be 3. So if I go up to n, what it will be? It will be n times c, okay? It will be n times c. For example, if you have 5 plus 5 plus 5 plus 5 plus 5 and so on, okay? If there are 4 5s, it's 4 times 5. If you have 7 5, then 7 times 5. That is the meaning of that. So sum of constant, if you are adding the constant like this, then it will be equal to n times c. We multiply those two, n times c. Okay, that is the first formula. Second one is this. Second is summation k goes from 1 through n, and then we also have a k there. Sum of k. We are adding this k from k equal to 1 through k equal to n. What is the meaning of this? You need to know. That is, you want to plug in k equal to 1. You are starting with k equal to 1, and you are adding. You are plugging k equal to 2, k equal to 3, and so on. So if I plug in k equal to 1, that's a 1. And then plus, if I plug in 2, it's 2. If I plug in 3, it's 3. If I plug in 4, it's 4. And we are continuing this all the way to the last one, that is n. So basically, this one is the sum of natural numbers, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, up to where? Up to n. You can add up to 10, you can add up to 20, you can add up to 50, wherever you want to go. Sum of natural numbers, this is equal to, so this sum is always equal to n times n plus 1 over 2. Okay, it is equal to n times n plus 1 over 2. Yes.
that always going to be equal to the A value in the problem?
Yes, we start with the initial value of 1 because we begin counting from 1, right? That's why we start from there. Yeah. And here, you can take quick example. For example, if I want you to add 1, 2, 3, 4, okay, without using the formula, how much is 1 plus 2 plus 3 plus 4? 10, right? If you plug in here, then you'll see n is equal to 4 if you want to go up to 4. 4 times 4 plus 1 is 5. 4 times 5 is 20. 20 divided by 2 is 10. Okay, so this formula works. N times n plus 1 over 2. Okay. Similarly, let's look at the third formula. Third formula is sum of or summation k equal to 1 through n. This time we want to look at k squared. So we are plugging in from 1 again, right? For k, but we have k squared. So it's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. Okay, if we go all the way down, then this is the sum of the square of the natural numbers, right? In the second formula here, we are just adding the natural numbers. In the third formula here, we are adding the square of the natural numbers. If we add the square of the natural numbers, it's given by this formula. It's interesting. N times n plus 1 and then 2n plus 1 divided by 6. That formula will give you the sum of the square of the natural numbers. And let's write one more. Summation k equal to 1 through n, k cubed. Sum of cubed, so it will be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way up to n cubed. If you add these cubes, this will be equal to n squared times n plus 1 squared over 4. In your node catcher, it is written as the square of this formula given in the second step, but when you square, that's the same thing, right? N squared, n plus 1 squared, and 2 squared will be 4. And we'll be using this when we try to evaluate the limit of the Riemann sum, because in the Riemann sum, the limit of the Riemann sum that I've written here in blue color, the value of the definite integral from a through b of the function with respect to x is limit as n approaches to infinity, then we have this summation k equal to 1 through n. And when you try to evaluate this definite integral, what we'll get is we are going to get one or more of these formulas, like sum of constant, sum of k squared, sum of k cubed. So when we get that, what you have to do is we have to use these formulas. Okay, we have to use these formulas to evaluate. That's why we need those formulas. And these are very powerful because if we start adding one by one, it's going to take a long time, but these short formula will make our work quicker and easier. Okay, before we jump into the example, any questions? No? Okay. Let's go to the problem then. Here is our question. The question is, evaluate the definite integral, which is given here, 1 through 4, x cubed plus 5x with respect to x using limit of Riemann sum. So if we want to evaluate the definite integral using limit of Riemann sum, you know the formula. Let me write here. Integration from a through b of a function with respect to x is equal to limit as n approaches to infinity, sum of k equal to 1 through n, f of xk times delta x. So what is that? This one, summation k equal to 1 through n, f of xk delta x. This is the Riemann sum. Okay, that is the Riemann sum. You can take any Riemann sum you want. You can do left Riemann sum, right Riemann sum, or midpoint Riemann sum. It really doesn't matter. Okay, but what you're doing is the n, that is number of subinterval you are taking, is very, very large. N approaches to infinity. And if we evaluate this, then we get the exact value of the definite integral. Okay, we'll get the exact value of the definite integral, not approximate, but exact. I know the math is going to be long here, but the result we are getting is accurate. Okay, so let's begin. So first thing, just like in Riemann sum, we have to find that Riemann sum portion first. So that is, we start with our function. Our function is x cubed plus 5x. That's our function. We need delta x. Delta x is b minus a over n. B is 4, minus a is 1. Over n, we don't know. N goes to infinity, right? So we'll keep n as n. N is a very large number. N approaches to infinity. So that becomes 3 over n. That becomes 3 over n. Now let's take this. Xk is equal to a plus k times delta x. A plus k times delta x. Which Riemann sum is this? Is this left Riemann sum? Right Riemann sum? Right Riemann sum, right? A plus k delta x, that's a right Riemann sum. Because if I use left Riemann sum, that will be k minus 1. And if I use the midpoint, it will be k minus half, right? And the limit of Riemann sum work for any Riemann sum. So I just want to take that simplified kind of expression just to make my work a little bit simple. It's not going to be that much simple, but a little bit. So I did a plus k times delta x. So I need to plug in those values. So a is 1 plus k times delta x. Delta x is 3 over n. And if you multiply by k, that will be 3k over n. Right? K times delta x. A times delta x is 3 over n. So k times 3 over n is 3k over n. So finally, we find f of xk. Let's do that. F of xk. That is, we have to plug into the function. We have x cubed, so 1 plus 3k over n cubed plus 5 times 1 plus 3k over n. Now, we have to simplify this. We have to simplify all this and then write as a single expression, single polynomial. And you can see the first one is 1 plus 3k over n cubed. That is, we have to multiply it 3 times. Right? We have to multiply it 3 times. And what you know from algebra is, let me write one formula. Formula from algebra. If you have 1 plus x cubed, 1 plus x cubed, you can quickly multiply and check it if you want, okay? But 1 plus x cubed is 1 plus x times 1 plus x times 1 plus x, right? Your result will be interesting. It will be 1, okay, plus 3x plus 3x squared plus x cubed. 1 plus x cubed will be equal to 1 plus 3x squared plus x cubed. So we are going to use this formula. We are going to use this formula to expand this one because it is just like that, right? 1 plus 3k over n cubed, right? Just like 1 plus x cubed. In place of x, I have 3k over n. So we can expand that using that formula. So if we want to expand that, let's see what we get. So first thing is 1, okay, plus 3x. So I can write 3 times 3k over n plus 3x squared, 3 times 3k over n squared plus x cubed, that is 3k over n cubed, right? Because when we expand this, we get 1, 2, 3, 4 terms. Exactly same thing 1, 2, 3, 4 terms. So 1 plus 3 times in place of x, 3k over n. And then we have 3x squared. So 3 times in place of x, we have 3k over n and then squared. And last we have x cubed. So x is 3k over n and then cubed. That is what we get from the first one. Now the second one, we have to distribute that 5. So if you distribute that 5 in the second one, what do we get? 5 times 1 is 5, and then plus 15k over n. Very good. Okay. Now let's combine the like terms. We have 1 in front, and second last term is 5. How much is 1 plus 5? 6. Let me write that 5 little nicely. 5. Okay, so that becomes 6. Then plus, let me point here with my mouse. If I multiply this, what I get? 3 times 3k over n. What is that equal to? 9k over n. And here we have 15k over n. 19k over n. I mean 9k over n plus 15k over n. How much is that equal to? 24. Okay, 24k over n. Okay, so we pretty much combine the like terms because the first term was like with the second last term, second term with the last term. Other two we can write as it is. Okay, if you look at the third term, we have 3 times 3 squared because that is squared, right? 3 times 3 squared is how much? 27, right? 3 squared is 9, so 27. So we can write that as 27, and we have k also is squared, n is also squared. And then the last term will be 3k over n cubed. If you cube that, 3 cubed is 27. Then k cubed over n cubed. Are you good so far? See, we have just done these 3 first step of Riemann sum. We found the delta x, we found xk, and we found f of xk. We have not even plugged into the formula. Okay, we have to plug into the formula for the Riemann sum, and then we have to take the limit. So long way to go. Okay, but we did the first part, first step here. So before I plug into the formula for the limit of Riemann sum, do you have any questions so far? No question? Okay. Now let's go to next page and then plug this into the formula. Okay. So what do we know is this? Let me write. Okay, I am writing that formula. We know the definite integral from a through b of the function with respect to x is the limit as n approaches to infinity, summation k equal to 1 through n, f of xk times delta x. That's our formula. So in our case, this will be, our value of the definite integral will be limit as n approaches to infinity, then summation k equal to 1 through n, no doubt on that. We got f of xk, right? We just got f of xk. So let's write down that f of xk. When I say f of xk, I'm talking about this one, right? Because we got that in the previous step. So we'll be able to use that. Okay. So let me bring that there. That is f of xk times delta x. F of xk should be multiplied with delta x. And what do we get as delta x in the previous slide? 3 over n. Okay. 3 over n. Now you can see the quantity inside the bracket and also outside the bracket, 3 over n. These are all variables, so we can technically multiply them. Okay. We can multiply them. We can distribute that 3 over n. So let's distribute 3 over n. Limit as n approaches to infinity. Summation k is from 1 through n. Okay. If we distribute, what do we get? 3 over n multiplied to 6. What is that equal to? 18 over n. Very good. And then plus, how much will be this one? 3 times 24. 72. Very good. 72 k over n. And then how much is 3 times 27? Is that 81? I mean, in the second one, when I multiply 3 over n, n is squared, right? N is squared, yeah. So 81 k squared over n cubed, right? And then the last one, if you distribute there, that will be 81 k cubed over n raised to 4. Are we good up to there? Okay. So now we are ready, but see, what is here? We have this big expression inside the bracket, and also we have limit and also summation. Okay, remember the limit and summation has two different variables. If you look at the summation, k is changing from 1 through n. That means in summation, k is the variable, k is changing. Okay, in summation, k is the variable, that is k is changing, n is fixed. But in limit, in case of limit, n goes to infinity, n is changing, right? Here, n is the variable. So that means first we are going to evaluate this quantity which is inside using the summation. Remember, when you're using the summation one more time, n is the constant. Okay, n is the constant. So let's see what this will give us. So we'll keep that limit as it is. This is equal to limit as n approaches to infinity. Now look at the first one. 18 over n for this summation. Summation k goes from 1 through n. So for this summation, k is the variable. But what we have here is 18 over n. 18 over n is a constant, right? And you know the sum of the constant is n times the constant, right? So that sum will be n times 18 over n if we use that formula. N times 18 over n. We use this formula. Let me show you. We use this first formula. Sum of constant is n times the constant, right? N times c. So we use that formula there. So sum of constant, sum of this constant is n times that constant. Okay. Now we'll go to the second term. If you look at the second term, 72 over n squared is constant, right? 72 over n squared is constant. So that means 72 over n squared is multiplied with the k. It's constant multiple. So in constant multiple, you keep that constant as it is, then multiply with sum of constant, sum of k from k equal to 1 through n. We have the formula. What is that? N times n plus 1 over 2, right? Sum of k, this formula, second formula there. Sum of k is n times n plus 1 over 2. So we use that formula there. Then plus, in the third one, we have 81 over n cubed, constant, then multiplied with, okay, 81 over n cubed is constant, multiplied with k squared, sum of k squared, k equal to 1 through n, k squared. You know the formula. What was that? N times n plus 1, then 2n plus 1 over 6. Very good. plus in the last one, 81 over n to the 4 is a constant. And then sum of k cubed is, if you look at your formula, it is n squared times n plus 1 squared over 4. Now look at the magic here. If you look at the step before this, the variables were n and also k, right? That's why inside the parenthesis, inside the bracket, you have n, also you have k. But now we use the sum. We are done with the sum. So once we are done with the sum, we just have the limit in front. See, we have limit as n approaches to infinity. So the variable should be n only. Do we have any k inside the parenthesis now? No, we are done with k. That's why the sum is not there. Okay. Great. Now we need to simplify this. This is beautiful. We can simplify this easily. Okay, we can simplify this easily if we try to simplify it carefully. Otherwise, it will be difficult. So I am going to write it as, let me write a little bit down. Okay, limit as n approaches to infinity. First one is just 18, is that right? Because n and n get cancelled. N get cancelled there. Now, so that is 18. Now, if you look at the next one, second term, look at the second term. You have 72 in the numerator, 2 in the denominator. What is 72 over 2? 36. So I can write that first. 36. 36 first. And then, after we write 36 there, this n cancels with one n, right? Here is n in the numerator, n in the denominator. That cancels. So only one n is remaining in the denominator. So that is n plus 1 over n. What is n plus 1 over n? N over n is 1, 1 plus 1 over n. That becomes 1 plus 1 over n. Or easy way to understand that, let me show you here using some side work. So you have n squared in the denominator, you have n times n plus 1 in the numerator, and n squared in the denominator, right? Pretty much that's what we have in our second term, n times n plus 1 in the numerator and n squared in the denominator, right? If I factor n from here, what it will be? If I factor n there, that becomes n squared 1 plus 1 over n squared. Because if I distribute that 1n, then we're just distributing 1. If we do that, n times 1 is n, and n times 1 over n is 1. Right? So those two cancel, we get 1 plus 1 over n. Beautiful there. So we are going to use that technique of factoring here so that we get those 1 over fraction. Now in the next one here, see in the third term, one more time. In the third term here, if you look at the number, we have 81 in the numerator, 6 in the denominator, 81 over 6. Can we reduce that fraction? 81 over 6 is how much? Reduce the fraction, not the decimal. 27 over 2. Okay. Say that again.
Please give a person to-
72. We in fact factor this n squared from here and cancel with that n squared. Yeah. Okay. We get 27 over 2 here. Now look here. One more time in this third term here. We have n times n plus 1 to n plus 1. If I factor n from the first one, okay, if I factor n from the first one, this will be n squared. If I factor n from the third term, this factor to n plus 1, then that becomes n cubed, right? N cubed cancel with n cubed. Make sense? If I factor n from here, this will be n squared. If I factor n from this one to n plus 1, that becomes n cubed. So n cubed cancel. And what remains? 1 plus 1 over n. Let's write it down. 1 plus 1 over n, and then 2 plus 1 over n. So what we did in third term, one more time, look at the third term. You can think on this in several different ways. Okay, you can think of this in several different ways. One other way of thinking this is like this. See, first of all, you have n times n plus 1, 2n plus 1, and then what is there in the denominator? N cubed, right? N cubed. You can think of that as n times n times n. You can also think of it like that. So n and n cancel. N plus 1 over n, and then 2n plus 1 over n. You can think of it in that way also. For n plus 1, the denominator is n. For 2n plus 1, the denominator is n. And if you separate the denominator in the first parenthesis, you get n over n plus 1 over n. And then the next one is 2n over n plus 1 over n. And if you cancel n and n, that's 1 plus 1 over n. And then n and n cancel, 2 plus 1 over n. It's up to you how you want to do your math. Okay. I just factored it because factoring looks much faster for me. So I get that. If you want to do it that way, that's totally fine. It will just take a few more steps, right? But it's still the same result because we have multiple ways of doing the math. So it's up to you how you want to do it. And then the last term, we have 81 over 4, which we cannot reduce. So I'll write that as 81 over 4. And if I look at this one, we have n plus 1 quantity squared. If I factor out n, it becomes n squared and come out. So n to the 4 cancel. I get, what I get is 1 plus 1 over n squared. But let me also show you using a different method. Maybe the method that you like. See, you have n squared, n plus 1 squared over n to the 4. Can we write n to the 4 like that? N squared, right? So the first part will get canceled. First part will get canceled. Now what is remaining is n plus 1 over n. All of them have a square. Because numerator is also squared, denominator is also squared, I can keep a single square there. And I can separate the denominator. So that becomes n over n plus 1 over n quantity squared. And n over n is 1. So that's why I wrote 1 plus 1 over n squared. So it's up to you how you want to do it. I just find factoring a little faster, but you don't have to do my method. You can do it in your own method. As long as you do the correct method, you are fine. Okay, now look at the beauty of this step. When I write like that, this becomes so beautiful because we have 1 over n everywhere, right? Do you see that? We have 1 over n everywhere. And when n approaches to infinity, what will be the value of 1 over n? 0. That's why. Okay, so we can do the direct substitution now. So 18 plus 36 times 1 plus 0 plus 27 over 2 times 1 plus 0, 2 plus 0 plus 81 over 4 times 1 plus 0 quantity squared. Now, please use your calculator there. Type that and tell me what you'll get. 18 plus 36 plus 27. See, this is 18, right? The first term is just 18. Second term is 36 only. 36. Third one is 27 over 2 times 2. That's just a 27. So it's like 18 plus 36 plus 27 plus 81 over 4. That is 20.25. Is 101.25. Is that right?
Yes.
Okay. So that is the exact value of the definite integral. And remember, while doing this, what we did is we use the limit of the Riemann sum. We use the Riemann sum, okay? We use the Riemann sum, and then we take the limit, because we know that if n goes to infinity, the result will be accurate, right? So this is the exact value of the definite integral that was given in that problem, 1 through 4, x cubed plus 5x. Okay? Any question, any concern, any comment? Yes. Why we get 0 again? Okay. The reason is n approaches to infinity, right? N is very large. So 1 over n, when you divide 1 by very, very large number, that is approximately 0, right? No worries. Yeah, you can take it. You are fine. You're fine. So don't worry, you are not recorded because only the screen is recorded. So you're fine. Okay. Any other question? No? Okay. So what we have done so far, if we want to, summarize this, in the previous class, we learned about Riemann sum, right? We learned about Riemann sum. We see left Riemann sum, right Riemann sum, and midpoint Riemann sum. Left Riemann sum basically underestimate, right Riemann sum overestimate, but midpoint Riemann sum, it was fairly accurate. That's what we said, right? It was fairly accurate, but not accurate. But the second thing we have noticed was if the number of subintervals n increases, the value become more and more accurate, whether it's left, right, or midpoint Riemann sum. So what we did today is we'll not be able to technically take 1 billion n and do the math. So instead of that, we take the limit. Okay, we found the Riemann sum, we keep n as n, and we take the limit as n approaches to infinity. And we got the result, and this is the accurate result. No more approximation there. This is the exact value of the definite integral. And remember, this process of finding the value of the definite integral, this is called the numerical integration. We are not doing any, reverse process of derivative here. Have we done that? No, right? We have not used the formula for antiderivative. We have not used the reverse process of differentiation here. Instead, we use numbers, we play with the number, we get the result. So this process of computing the antiderivative or integral, it's called the numerical integration. Okay, so we have just done one type of numerical integration in calculus 1. In calculus 2, we'll do few more. Maybe we'll do trapezoid rule and Simpson's rule. Okay, those are two additional rules that you'll see in calculus 2, and they are also numerical integration. One more time, they are trapezoid rule and Simpson's rule. Okay, we did Riemann sum here. Okay, limit of the Riemann sum is the first way of doing it. Second way, trapezoid rule. Third way, Simpson's rule. Okay, great. So we can find the definite integral using numerical integration. We can find the value of the definite integral using numerical integration. And the type of numerical integration we explored here is the Riemann sum. Now, the other way of computing the definite integral is using geometry. If the shape determined by the integral, okay, if the shape determined by the integral is a regular geometric figure, we can find using some geometric formula. Any question or anything? No, okay, good. Oh, we just get into some easy formulas here. Evaluate the following definite integral using geometry. So first one, you can see we have to integrate from 1 through 3, 3x plus 2 with respect to x. What we have to do is we have to graph this integrand function. We have to graph this function 3x plus 2. If you want, you can use your calculator to help you with that graphing. So please use your calculator and then try to sketch the graph. X plus 2 is a linear function, right? It's a linear function with y-intercept of 2 and slope 3. That means the graph will be something like that. That is y equal to 3x plus 2. And we have to integrate. If you look at this one, We are integrating this from x equal to 1 up to x equal to 3. Integrating from x equal to 1 up to x equal to 3. So let's show that. X equal to 1 is somewhere here. And x equal to 3, maybe it is somewhere there. And that definite integral will be equal to this enclosed area. Right? It is equal to that enclosed area. What is this shape? What do you see here? Trapezoid, right? It's a trapezoid. So that definite integral, integration from 1 through 3 of 3x plus 2 dx is equal to area of that trapezoid, which is base times height 1 plus height 2 divided by 2. That's our formula. To find the area of the trapezoid, it is the base of the trapezoid, which is this one down here from 1 through 3. So what is the base there? What do you see? How long is the base of the trapezoid there? 2 units. That's right. From 1 up to 3, that's 2 units. And what is this first height? To find the first height, we have to plug in 1 into the function. So it will be 3 times 1 plus 2. What is that equal to? 5. Okay, very good. That is 5. And what is the second height? You plug in 3. 11. Very good. Very good. So the area will be, let me plug in here, base is 2 times the sum of the height, 11 plus 5 is 16, divided by 2, that's equal to 16. Is that right? Okay, so the value of that definite integral is 16. Remember, what we did here is not much different from the previous example. In previous example, we found the value of definite integral using the limit of Riemann sum. That's why that was long, right? But here, the shape was a regular geometric shape. If it is a regular geometric shape, we can use the formula from geometry and calculate the definite integral just that fast. Okay? Now, next one. See, we have to integrate from 2 through 3 square root of 1 minus x minus 3 quantity squared with respect to x. You can use your calculator to help you draw the graph. So please try and see whatever graph you'll get. Do you get a semicircle, half of a circle in your calculator? Yeah, if you zoom in a little bit, you should get half of a circle or semicircle, something like that. Right? You should get a semicircle, which is above the x-axis. And where is the center? If you look at that diagram carefully in your calculator, is the center at 0, 3? Okay. Yeah, it's 0, 3. So this is 3. Let me label like this. This is 3. This is 1. No, let me don't label. It's okay. Let me label like this. 3, 0. Let me just label like that. 3, 0. And the radius is 1, right? Right? Radius is 1 because here is 1. So radius must be 1. So if you look at that carefully, the radius is 1. So we draw this graph using our calculator, right? Using our calculator. But you can also think of this function as y equal to, let me write here in the side. So you understand this, y equal to, we have square root of 1 minus x minus 3 squared. If we analyze this, you'll see that this is a semicircle. Here we have the positive square root. So the y value is positive only. That's why it is above the x-axis. And if I square this on both sides, if I square it on both sides, that becomes y squared. Y squared is equal to 1 minus x minus 3 squared. Right? If I square it on both sides, that becomes y squared. Right hand side square root will go away. And then if I add x minus 3 quantity squared on both sides, it will be x minus 3 quantity squared, then plus y squared. Y can be written as y minus 0 squared equal to 1. 1 is same as 1 squared. And if you look at this equation carefully, this is the equation that you know from your pre-calculus. It's like x minus h squared plus y minus k squared equal to r squared. If it is x minus h squared plus y minus k squared equal to r squared, that's a circle with center at 3, 0, right? And radius 1. That's exactly what we got. So if the radius is 1, that means if this point is 3, this must be 2, right? That is 2, 0. So that is 2, 0. This one is 2, 0. Right? That's 2, 0. My 0 is not looking nice. 0, there you go. And what we want to do is, we want to evaluate from 2 up to 3. We want to evaluate from 2 up to 3. Area is, integration is same as the area. So basically, we want to find that area from 2 up to 3. Do you see that? So that definite integral is equal to this area. Okay, that definite integral is equal to that area. Right? And this is the area of a quarter circle. Not the whole circle, not the semicircle, but 1/4 of the circle, right? And the formula for area is pi r squared. But here we are taking 1/4 of that. So which is equal to pi times radius is 1 squared over 4. So what is the value of that integral? Pi over 4. Okay. So when we integrate this, our answer will be pi over 4. So if we have geometric shape, you can see that the calculation is very easy. Why
are you divided by 4?
Because it is 1/4 of a circle. It's not a whole circle. Area of the whole circle is pi r squared. And this is only 1/4, right? So we divide the total area by 4. So this process is the geometric method of computing the area. So if you try to recall back on what we did for about an hour today, we learned how to evaluate the definite integral. Okay, using 2 different methods. The first method is using the limit of the Riemann sum. Right? First method is using the limit of the Riemann sum. We find the Riemann sum using n, where n goes to infinity. N is very large. Okay, in that, we have to use a lot of summation formulas. But this one is quite easy because the area determined by the integral function here forms a regular geometric shape. If the shape is a regular geometric shape, we can basically use the formula and find the area. But if the shape is not the regular, then Riemann sum will definitely work, or we have to use some other technique of evaluating the definite integral. Maybe we have to use that inverse process of differentiation. Any question? Okay, if you have no question, we are going to end the first half of the class.